had to, our engineers had to develop the software, and that software development, interlocks, everything, monitoring, controls was carried out in-house at PCC, and we finally got the bid. And not only we got the bid, we also produced the PET isotope F18 by bombarding, by irradiating the O18 enriched water at the target PET area. So after that, the IBM people, they contacted us, and after that they helped us and they supplied the software. Now we have the two softwares. We have kept our software, so this is the IBA software we are using now, standard software. And this is the clean room where 2 paid hot cells are there, and there are 7 spec hot cells. Now we have already produced Helium-201, which is used for myocardial perfusion. That has been, I will go to the next slide. Gallium-67, Gallium-68, fluorine, that is FDG, fluorine-18, F18NA, sodium fluoride, and now near future our plan is to make this Germanium-68 to Gallium-68 generator, and also Palladium-103, and we are also in the process of adding one component to get the Iodine-123, and also we have a plan for Indium-111. So these are the 5 green lights already I have mentioned. So now the summary of the radioisotope production, that is commercial production started in June 2020 for FDG, and the Gallium-68 PSMA already started. So 18F, NAF, sodium fluoride for bone scanning, etc. It is required, that is going on. And one thing I can tell you that this is basically, we are facilitating the machine to the industrial arm of BAE, BRIC. So they produce and sell the isotopes, and they sell at a very, very affordable price, which is, say, for example, FDG in Calcutta, from private party, if it is purchased, one dose of 10 millipuri, if it is 6,000 rupees, but BRIC is supplying at 2,000 rupees, so almost 1/3 the price. And Gallium-68 PSMA, BRIC is supplying at around 12,000 rupees per dose, which is approximately about 21,000 to 28,000 per dose in the market, in the private market. So also I have already mentioned Gallium-67 cyclate, Helium-201 fluoride. So these are the bone scanning example, which is already done at the Indian Army's Command Hospital, Kolkata. So these are the picture of that. It's a very nice result has been obtained, and they have shared their things. And this sodium fluoride, actually it is as compared to technetium 99 and technetium, this MDP, it is better because you need a much lower dose as compared to technetium 99 MDP. So uptake is much less, but less radioactive exposure, almost 1/3 of the conventional technique. So this is the Thallium-201 that has been supplied to hospitals, and the Rabindranath Tagore International Institute of Cardiac Science, Kolkata, and this is the picture of a patient. These large images of the biodistribution carried out of patients at these hospitals. And this is the Gallium-68 PSMA. This is commercially supplied to the hospitals of Kolkata, very near to Kolkata. This is the picture from, this picture is from this Command Hospital, and also we have got from another Netaji Subhas Cancer Hospital. They have shared the picture. So besides the medical applications, we are also using There is medical cyclotron. This is 30 MeV proton beam, and this current is a very high current machine. So there is a we use also for the material science activities, as well as there is another beam line which is for the we call it a fifth beam line, which is to be used by BRC for ADSS target study. These are the material science beam lines installed there. So these are some target holder etc. has been developed at DECC for material science beam handling and target handling. So how to focus the beam or defocus the beam, that development has been done at DECC itself. And these are the various, you see, this is the, we call it a rapid facility, shuttle facility, where when the solid target, solid target is irradiated, after that it goes to the hot cell, it is going through this. And here, the thing is that the target is in a structure. So that structure it is going through this pipe. And this is it's a long distance it's going. And this is going using this pressure, in air pressure. So that there is a pressure sensor. If this irradiated object is stuck somewhere, there is a facility to check whether it is stuck, where it is stuck. So from the pressure sensor, it goes to the control room computer, and there we can find out that this position it is stuck. So there we are taking all the safety precautions from the health physics. We have to take out that stuck system, target system. Now I am coming to, these are the three cyclotrons I have already mentioned. Now I am coming to the another accelerator, although this is not a cyclotron. This is for the radioactive ion beam facility, using the primary beams from K130 cyclotron. So we have the K130 cyclotron here. So in this campus this is situated. And from this K130 cyclotron beam it is going to this. This is the RIV facility, where now this facility in the first phase 1. So our aim is to get a 1 MeV per nuclear. So right now we are getting the beam up to after this one. And then L4 and L5 that is already installed, but we are not yet done experiment after that. We have done experiment before that. So up to 450 keV per nuclear we have been delivering to the UGC, DAECS user, different students from different university of India. So that is being utilized, the RIV as well as stable beam. So this is the more clear picture. So these are the components it is installed there. So this is the actual picture where all the components like different focusing element, beam line focusing elements, etc. is shown here. So this is the installation and testing of a low. There are different components. So this is the installation and testing of low energy beam transport line connecting to 1+ ECR and 6.4 gigahertz and 2.45 gigahertz that is completed. This is the closer view of this 1+ ECR, 2.45 gigahertz and dipole magnet. And these are the installation of beam diagnostic stations and measurement of transverse profile for 100 kV electron beam is completed. This is the picture for that. And after that, there are some recent use of these RIV facilities. So study of angular patterning and nanopatterning of muscophile mica using ion beams from RIV facility that has been used. And this is the isolated silver nanodot formation by silver ion implantation of nanopattern silicon nitride template. So these are the few uses recently done at this RIV facility. Now we have a future plan for RIV facility. that is we call it a ONURI, Advanced National Facility for Unstable and Rare Isotope Beams. Here you see, this is our aim is to get 100 MeV per nucleon, but our plan is to build it at our Rajarhat campus. I have already shown in a Google map. So these are, but in this big picture, there are very few components which we are already, which we have already developed for our RIP facility, and we have to extend or we have to replicate many of the components for getting the up to the 100 MeV. Where there is our plan is to make a big cyclotron after the RIP to get 100 MeV. And also we have a plan to have this superconducting electron MMAP MeV in this line, or 50 MeV proton driver. There are two paths in the route, so we are still deciding which path we have to take. Now I am coming to a very few examples of utilization of cyclotrons, recent utilization, because it is being utilized for the last 45 years. So recent utilization I have been just showing. So these are the experiments performed using alpha beam with gamma array. Various experiments. We have an infrastructure for various infrastructure for, as you know, there are different detectors. So there are the monster detector, Inga array, etc. So these are the some structure detectors, array of 11 bumpers surface global APV detectors. So various users are there. These have been done in collaboration with BCC, SIMP and UGCD, ACSR. So there we have used the alpha beam from K130 cyclotron, and these are the various experiments have been done. Now here I want to mention that a ERL paper has been published with this about this in C, observation of exotic mode of excitation oblique in gold 183. Here actually this uniqueness of this experiment was the only instance in which the multiple transverse oblique bands in the same nucleus have been identified. Two different behaviors of oblique energy spin, both increase and decrease, observed for the first time. So this paper has been published in ERL. So here actually we have used this neon 20 beam 146 MeV from our cyclotron, and it is radiated on this beam was hitting on this gold to 183. Sorry, gold 183 was formed in technetium 169 using the neon beam. There is 6 neutron turns out. And besides this, there are many experiments have been done. I have shown a very few because within this time limit I have to complete. So these are the various material science activities for irradiation studies have been done. This is the microstructural characterization and mechanical property measurements of proton irradiated niobium, zirconium, carbon alloy. These are some requirements. This is a collaboration with DRC. So using the 7 MeV proton beam, 3 microampere, the testing has been done, experiment has been done.
Shumin.
Yes, right. So these are the experiments done using this material science activity has been done. So with this, I acknowledge the thankful to BC scientists, engineers, technical staff, also the administration, accounts, security, transport, fire service, everybody, fire services, purchase stores, housekeeping, gardening, for their valuable contributions to that. So thank you very much.
I think we have very little time for a question. Just K150 cyclotron and that is super conducting K500. What will be the power requirement of that?
Yeah, A130 cyclotron, for only the power requirement is reduces for the superconducting magnet. But you have to understand that superconducting magnet, although the power requirement is very less, of the order of say 1, but one thing you have to do, you have to also fill the helium. So you have a power requirement. It is not that as you are making it superconducting, so almost the resistance is very low. That is okay, but actually for helium plant operation, because you have to generate the liquid helium. So helium plant operation power requirement is there. So it is not that it is 110. It is for magnet. It is of the order of say less than half. But here you mind it that we are getting the magnetic field of 5 Tesla. But there, K130 cyclotron, we are getting, using double the power, we are getting only 1.7 Tesla for routine. So,
Okay, it may be watt, say 500 watt or 200 watt, something like that.
superconducting, you are talking about superconducting?
K130.
K130 is of the order of around 500, not 500 watt, is a kilowatt. It is of the order of megawatt.
Megawatt. How many megawatt? 1.2.
It is around 0.8 megawatt or so.
0.8 megawatt and
For 800 kilowatt.
800 kilowatt. And that of K500?
K500, that is around 400 to like that, 400 to 500.
Watt.
No, kilowatt.
Kilowatt. Achha, achha. Okay. Okay, let us thank the speaker once again.
Thank you.
The next talk is by Dr. Shoji Nagamiya. It will be online talk.